Hello students, welcome to my today's video lecture. Myself, Dr. Leena Norona, working as junior lecturer in Swami Vivekanand Shikshan Sanstha's Vivekanand College, Kolhapur. Today, I am going to discuss Chapter 5, Electrochemistry from 12th Chemistry. As per State Board exam, this topic carries 5/7 marks. Chapter 5, Electrochemistry. Let us see few examples of electrochemical cells. First is Daniell cell. It was the first electrochemical cell discovered by Alexander Volta and Luigi Galvani, followed by Daniell. This cell is also called as galvanic cell or voltaic cell. Next cell is a dry cell. You must have observed this cell in portable radios, tape recorders, clocks and flashlights. Another cell is nickel cadmium cell. It is used in photography equipments, flashlights and portable electronic devices. The next is lead storage battery, commonly used in automobiles and inverters. In today's lecture, we will study the concept of redox reaction, conductors, its types of conduction, types of electrolytes, conductivity, resistivity and molar conductivity. Beginning first with the definition of electrochemistry. What is electrochemistry? Electrochemistry is the branch of physical chemistry which deals with interconversion of chemical energy and electrical energy. It also deals with the resistance and conductance of aqueous electrolytic solutions. The determination of conductivities of aqueous electrolytic solutions provide information on the extent of ionization of electrolytes in water. Electrolysis is another process in which breaking of an ionic compound takes place by the passage of electricity. Here, electrical energy is converted into chemical energy. Examples: electrochemical process, electro-refining for purification of metals, electroplating for coating one metal on the surface of another. Electrolysis examples are preparation of NaOH, fluorine and electrolysis of NaCl. Redox reaction forms the basis for generation of electricity by chemical reactions and also for chemical reactions taking place by means of electricity. These reactions are carried out in an electrochemical cell. What is redox reaction? The reaction which involves both oxidation and reduction processes are called redox reactions. Oxidation, the process which involves loss of electrons, is called an oxidation process. Example, Na solid loses an electron to form Na plus cation. Next is reduction process. The process in which gain of electrons takes place is called reduction. In this, the example can be given as chlorine gas accepts 2 electrons to form twice chloride anion. We should also know two types of substances which help in redox reactions. One is oxidizing agent. The substance that can gain electrons is called an oxidizing agent. Example, F2O2, Fe3+, H2O2, HNO3, KMNO4, K2Cr2O7, etc. Next substance is a reducing agent. The substance that can lose electrons is called a reducing agent. Examples are all metals like sodium, magnesium, aluminium, cations, SO2, SnCl2, carbon monoxide, hydrogen gas, carbon, etc. Next term which is required to understand redox reaction is an oxidation number. It is the numerical charge plus or minus assigned to an atom or ion in a molecule. Redox reaction can be explained with the help of the following example. SnCl2 plus 2 times FeCl3 gives SnCl4 plus 2 times FeCl2. In this example, we find oxidation number of tin in SnCl2 is plus 2, which increases upon formation of SnCl4 as Sn plus 4. That means oxidation number of tin has increased from plus 2 to plus 4. So, Sn plus 2 is oxidized to Sn plus 4. We also find in FeCl3, oxidation number of Fe is plus 3. When the reaction is performed and product obtained is FeCl2, oxidation number of Fe changes to plus 2. That means oxidation number of Fe has decreased from plus 3 to plus 2. So Fe is reduced from plus 3 to plus 2. Now let us study about conductors. The substances that allows the flow of electricity or charge transfer are called conductors. There are two types of conductors. First one is electronic conductors. The conductors in which flow of electricity is by migration of electrons through the conductor are called electronic conductors. Next type is electrolytic conductors. The conductors in which flow of electric current is by the movement of ions of the electrolytes are called electrolytic conductors. Now let us study the distinction between electronic conductors and electrolytic conductors. This point is important regarding board exam point of view. This question, if asked, carries 2 marks in this exam. Now let us see about the distinction between these conductors. In electronic conductors, flow of electricity is by migration of electrons through the metallic conductor. In electrolytic conductors, flow of electricity is by migration of cations and anions. In electronic conductors, no transfer of matter takes place. In electrolytic conductors, transfer of matter takes place. In electronic conductors, no chemical changes take place during the process. In electrolytic conductors, chemical changes take place when current flows. In electronic conductors, resistance of conductor increases with increase in temperature. In electrolytic conductors, resistance of conductor decreases with increase in the temperature. Conductivity decreases with the temperature increase in electronic conductors, whereas in electrolytic conductors, conductivity increases as temperature increases. Few examples of electronic conductors are solid and molten metals. Examples of electrolytic conductors are solution of ionic salts and aqueous solutions of acids and bases. Next we study about metallic conduction. Electrical conduction through metals involves direct flow of electrons from one point to another. The outermost electrons of metals form conduction band. The electrons in the conduction band are free to move and hence flow under the influence of applied electrical potential. Thus, metallic conductors are electronic conductors. The next type that we are going to study is electrolytic or ionic conduction. In this type of conduction, the charge transfer occurs in the form of movement of ions through molten electrolytes or aqueous solutions of electrolytes. Electrolytes such as ionic salts, strong or weak acids and bases dissociate into ions when dissolved in polar solvents such as water. Example, KCl, acetic acid, sodium hydroxide, HCl, etc. Ionic solids dissociate even in molten state. Now let us study about electrolytes. What is a non-electrolyte? Substances which do not dissociate into ions in aqueous solutions and do not conduct electricity are called non-electrolytes. Example, sucrose, urea. These are organic substances which are soluble in water but they do not form ions. Therefore, they become examples of non-electrolytes. Next type is strong electrolyte. The substances such as ionic salts, strong acids and bases dissociate completely in aqueous solutions and are called strong electrolytes. They have high conductivity. Examples, HCl, NaOH, KOH, HNO3, etc. Another electrolyte is a weak electrolyte. Weak acids and weak bases dissociate to a very small extent in aqueous solutions and are called weak electrolytes. they have lower conductivities than strong electrolytes. Examples: acetic acid, ammonium hydroxide, HCN, etc. You have been hearing about conductance in the past points. To understand this concept, we must know, first of all, what is resistance, what is resistivity, what is conductance, and then what is conductivity. So let us study about electrical conductance of a solution. To know this, we must know what is resistance. The measure of opposition shown by any substance to an electrical flow is called resistance. According to Ohm's law, R is equal to V upon I, where R is equal to electrical resistance. It is measured in ohms. V is equal to electrical potential difference, which is measured in volts. I is electric current, which is measured in amperes. Now, the resistance of a conductor is directly proportional to the length of the conductor and inversely proportional to the area of cross section of that conductor. Therefore, we write the relation as R proportional to L upon A. Now, R is equal to rho L upon A. Let us call this as equation number 1. In this equation 1, the symbol rho, which we call proportionality constant, is also termed as resistivity of the conductor. You know about L. It is equal to length of the conductor, and A, it is equal to cross-sectional area of that conductor. Very often, the definition of rho, that is resistivity, is also asked. So we should remember, if L is taken as 1 meter or 1 centimeter and A is taken as 1 meter square or 1 centimeter square, then that resistivity is the resistance of the conductor of unit length and unit cross-sectional area, because R becomes equal to rho. Now we shift to the next term, that is called conductivity. The term conductivity is denoted by the letter kappa, the symbol kappa. To understand this concept, we must first know about conductance. Conductance is denoted by the symbol G. The reciprocal of resistance is called electrical conductance of a solution. Mathematically, we write conductance as G is equal to 1 upon R. But G is directly proportional to area of the conductor, that is cross-sectional area of the conductor, and inversely proportional to length of that conductor. Therefore, G can be written as G is equal to kappa into A divided by L. Let us call this as equation number 1. If L is taken as 1 meter and A as 1 meter square, kappa becomes equal to G. That means conductivity and conductance are equalized. Equation 1 can also be rearranged and written as kappa is equal to G into L divided by A. Hence, K is equal to 1 upon R, as G is equal to 1 upon R. So we write it as K or kappa is equal to 1 upon R into L upon A. Let us call this as equation number 2. Now from equations 1 and equation 2, we get the final relation as kappa is equal to 1 upon rho. Let us see various definitions of the term conductivity. Conductivity is the electrical conductance of a conductor of unit length and unit area of cross section. Or conductivity is the electrical conductance of unit cube of material. Or conductivity is also the electrical conductance of unit volume 1 meter cube or 1 centimeter cube of a solution. Now let us study about several units of electrolytic conductivity. Quantity, SI unit, common unit. Quantity number 1 is length. Its SI unit is meter, common unit is centimeter. Area, SI unit is meter square, common unit is centimeter square. Resistance, SI unit is omega, common unit is also omega. Conductance, SI unit is Siemens, that is denoted by capital S or per ohm. Conductance was also measured in mhos. Next term is resistivity. SI unit is ohm meter, common unit ohm centimeter. Another term is conductivity. SI unit per ohm per meter or Siemens m raised to minus 1. Common unit per ohm per centimeter. Now let us study about another important term, which is molar conductivity. First we should know what is the need of molar conductivity. Electrolytic conductivity is not suitable for comparing conductivities of different solutions. The solution of higher concentration contains more ions and has higher conductivity than the solution of lower concentration. In 1880, George Colebrook introduced the term molar conductivity, which is denoted by capital lambda symbol. The definition of molar conductivity can be written as ratio of electrolytic conductivity kappa to the molar concentration C. Mathematically, it can be expressed as lambda is equal to kappa upon C. SI units of kappa are Siemens meter raised to minus 1 and that of concentration are mole m raised to minus 3. Hence, SI unit of lambda becomes Siemens meter square per mole. Common unit of molar conductivity is per ohm centimeter square per mole. Now let us know the significance of molar conductivity. The conductance of a volume of a solution containing 1 mole of dissolved electrolyte placed between two parallel electrodes 1 centimeter apart and large enough to accommodate is the molar conductivity of that electrolyte. We can define conductivity also as electrical conductance due to the ions in 1 centimeter cube of a given solution. Now let us study an important relation between kappa, that is electrical conductivity, and lambda, that is molar conductivity. Conductivity kappa is the electrical conductance of 1 centimeter cube of a solution. If V is the volume of solution taken in centimeter cube containing 1 mole of dissolved electrolyte. Its electrical conductivity becomes equal to lambda. Each 1 centimeter cube portion in the volume V has conductance kappa. So, lambda is equal to kappa into V. Let us call this as equation 1. We know that concentration of solution is equal to C in mole per liter. Concentration of solution can also be written as C mole per liter upon 1000 centimeter cube per liter, which is also equal to C upon 1000 mole centimeter raised to minus 3. All of us know that reciprocal of concentration is equal to V, that is volume. So V can be written as 1000 upon C centimeter cube per mole. Let us call this as equation number 2. Putting the value for V in equation 1, we can get an important relation, that is lambda is equal to 1000 kappa upon C, or lambda is equal to 1000 K upon C. Numericals based on this particular relation are very often asked for 2 marks for board exam. While solving several numericals on conductivity and molar conductivity, we should know another important term which is called a cell constant. So what is cell constant? What is its unit? How is it determined? Let us see in brief about it. The cell constant is defined as the ratio of distance between the electrodes to the area of cross section of the electrode. Cell constant is equal to small b is equal to L upon A. That means cell constant is indicated with small letter b. In order to express cell constant, per meter or per centimeter is used. The conductivity of an electrolytic solution is given by the equation kappa or K is equal to 1 upon R into L upon A, which we have studied previously. But we know that G is equal to 1 upon R. Also, G is proportional to A upon L. Therefore, G becomes equal to kappa into A upon L, or G is equal to K into A upon L. So, K becomes equal to G into L upon A, that is equal to 1 upon R into L upon A. Therefore, K or kappa becomes equal to B upon R. Both the relations cell constant is equal to B is equal to L upon A and K is equal to B upon R are important while solving numericals. On today's concept, let us see what is your today's exercise or homework. Question 1. Definition, 1 mark each. Define number 1, conductivity. Number 2, resistivity. Number 3, molar conductivity. Number 4, electrolysis. Number 5, strong electrolyte. 6, non-electrolyte. 7, conductance. 8, ionic conduction. Another question for 2 marks. Question number 2. Distinguish between electronic and electrolytic conductors. Question 3. Explain the relation between conductivity and molar conductivity for 2 marks. Question 4. State the SI unit of 1 mark each. Conductivity, molar conductivity, resistivity. Question 5. Write the significance of molar conductivity. 1 mark. Thank you.